Hey, what's going on, guys? CodeMonkeyGames here. In this video we're going to implement a couple more randomizing routines in order to eventually generate the candidates serving as the magic numbers, and we would be using those candidates within the routine to generate this magic numbers for magic bitboards. So in order to approach in this sort of way, I would like to reference fitting in randoms kind of section within the looking for magics article on the chess program in Wikipedia, and here we have the source code by Tord Romstad, who is known as the author of the Stockfish chess engine, and he suggests just run out random numbers with a low number of non-zero bits until you find a number which works. Is by far the fastest and easiest ways to generate the magic numbers, even though they have created even better way, like probably Marco Costelba mentioned. He has created some even faster way of doing things, but as far as now we'll have quite pretty fast processors. This method by Tord is quite pretty nice, and it works like a charm. So bearing this idea, so that we need a low number of non-zero bits, we'll actually go and start writing some code. But before that, I just want to show you this visually to get you an idea of what is this all about when we talk about the low number of non-zero bits. So let me just try to open the terminal in the current working directory, and by typing make debug, and if it compiles, I want to run the BBC binary executable. Okay, and here I just want to print a bitboard, and I will use my get random. Well, by the way, we did call this function like get random number, but let's give it a slightly different name. Let's call this U32 number, which stands for unsigned 32 number, because the second function would be called like get random U64 number. So here I can simply say get random U32 number, and just bear in mind that it returns the 32-bit number. We also need to explicitly convert this to U64 type to fit. Oh my god, what am I doing? Obviously not in initializing a text. I'm sorry, guys. We need this to do within the print bitboard. I'm sorry. So now we have this visual representation of the randomly generated number, and this is the decimal representation, while here we have this binary representation printed as a bitboard. And in order to do what they call as the random number with a low level of non-zero bits, we can simply slice. So here I can say like slice. Well, I call this upper 16 bits. Probably not the most accurate way to call this, but I'll just give you an idea of what I mean by saying this. So by saying upper, I mean from most significant first bit site, and if we just bitwise end with a constant of 0 and FFFF, so 16 bits. So yeah, with this 16 bits here, and let's have a look how it looks basically. So yeah, I would also need to hold on a sec. Yeah. So you see, like here we have the least significant bit, and then the number is growing, and here we have the most significant bit. So from well, obviously regarding this bitboard representation, the most significant site is from the bottom, not from the top, and this like slice upper might confuse you a little bit, but that's the reason I'm mentioning from the most significant first bit site. So here we have the most significant first bit. So from this site, from the top, from the upper part of the integer itself. I'm sorry, just my terms are not really that scientific or something. Anyway, the idea that we're slicing the upper 16 bits. So I just really hope that I really want to rely on this visual explanation, because yeah, my English is too poor to describe this in a proper way. I'm sorry for that, guys. So what we did obtain here, we did reduce the number of non-zero bits, so of this once literally, and that's kind of our goal. So now, bearing this idea in mind, and also, yeah, obviously we have, if we have a look at the decimal representation of the number resultant after this operation, it's significantly smaller compared to this one, obviously. So bearing in mind this idea, we'll now go for implementing our generate 64-bit pseudo-legal numbers function. Okay, so this already would be U64, and call this get random U64 numbers, just like this. So the very first thing to consider, we'll define 4 random numbers. It probably doesn't really matter that much. I'm just following the towards implementation here, and I would be showing you how this works in the process of writing this. To be honest, I didn't play around with different number of numbers, but this approach works quite pretty nicely, because the shuffling seems to be enough to at least to generate the magic numbers. So that's the reason why we're going for this. So let's create the U64 and number 1, number 2, number 3, and number 4 variables. And now we need to initialize our random numbers. So here we have number 1 would be equal to get random U32 numbers, number in single, and we want to make this a U64 type, and also we want to bitwise and the resulting number with its constants, just to slice this 16 bits. Let's say slicing 16 bits from most significant first bit side. I really hope that this commentary is quite pretty clear, like regarding what in particular we're doing right over in here. Okay, so and now we need to do the same thing with all the 4 numbers here, and here we want actually to return a random number, and we'll go for shuffling this even more. So we would be bitwise ORing these numbers in the following way. So number 1 bitwise OR with number 2 left shifted to 16 bits, and then bitwise OR with number 3 left shifted to 32 bits, and bitwise OR with the number 4 left shifted to 48 bits. And this is so before returning the candidate for a number, it's not even the candidate for a number still, it's just a number that would be used in order to generate the candidate, like that. So we need even more bitwise operations to shuffle things, and simply to shuffle the bits even more. Okay, and well, we can actually print we can now print a bitboard. By the way, the more proper way is to say like this actually. I hope the result is not really gonna be different, or I'm just wondering, hold on a sec. what have I done? Okay. So yeah, the number seems to be the same as it was before, right? Well, at least visually it does. Yeah, 6, 4, 8, 9. Yeah, 8, 9, 0. Yeah, this is it. So we can now go for. We don't actually even need these guys anymore, but let's keep them for a while. So if we now print this bitboard type, kind of resulted by the get random U64 number, and have a look at this. Okay. Spell this. Oh, numbers. Why call this numbers? This has to be a number. Okay. Then this is this is how the bitboard looks like. So just showing you how it looks like, basically. Okay, and one last thing that one last operation that we would be doing before claiming the number to be ready to serve as the candidate to become a magic number. We will bitwise OR the result 3 times, like this. And in this case, so let me just compare them kind of again. So print bitboard and this get random number. Okay, so this is how it looks after returning the U64 random number, and this is how we reduce the number of non-zero bits again using this double bitwise AND operation. So this is how the candidate to serve as a magic number would eventually look like. So this is it, basically. And the very last thing left here is actually to make this a function, copy, and let's call the function generate magic number candidate. So this would be U64. Let's call this simply generate magic number. Okay, and here we can simply return this double bitwise ANDed, or maybe I should say triple bitwise ANDed. I'm not sure how to count this, to be honest, but doesn't matter really. So generate magic number candidate. So if we now just here say like generate magic number, we'll have absolutely the same stuff, but already while calling the function. So this like bitboards from the bitboard perspective, or this like numbers would serve as a potential candidates to serve as the potential magic numbers. Actually, this is kind of it, guys. So quite pretty simple. And the very last thing I would like to do within this video is just to put this randomizing routines to the proper place within the source code. And let me just go to probably where the attacks starts, or maybe even, I'm not sure what would be the most proper way, a proper place for placing this. You know, like I would probably even create a separate section for them. Copy, and here let's call this random numbers, like this. So just to give them a separate section within the source code. I'm not really that sure if we're supposed to be reusing this routine somewhere else in the source code in future, but at least for now I think it's quite pretty nice to have them separated like this. So yeah. Okay, so I just want to run the source code for the one last time to make sure nothing was lost. Yeah, it seems like it, so it's quite pretty nice. And this is it for this video, guys, basically. So I guess starting from the next video we can already create a routine to test these magic numbers, whether they work or not, and that is going to be quite pretty complicated routine, so I need to prepare it a little bit. I mean, I've already written this obviously, but I just need to walk through this a couple more times to make sure that I would be providing the most reasonable explanation regarding how exactly the code works, basically. Well, okay guys, so this is it from my side. Thanks for watching. I really appreciate the fact that you're following this series and paying attention, and the interest is actually growing. The interest in my work is growing. This is really pleasant, to be honest, and a bit flattering even. So see you next video, guys. Until then, and take care.